Welcome once again to the lecture of topology. It is the 8th lecture in series about the topic separation axiom. Till now you know what is a T0 space, what is a T1 space, what is a T2 space. We have done several theorems on T0, T1 and T2 space, and we are continuing on the same. The first theorem what we are going to do today, first I'll write the statement of the theorem and then we will prove. So what the statement of the theorem is, if F is a continuous map from a topological space X top to another topological space Y row, and Y row is given to be T2. So you can write from X top to T2 space. So you can add here T2 space from X top to T2 space Y row, then the graph of the function f is a closed subset of x cross y. This is the theorem what we are to prove right now. So first of all, try to understand which set we are talking about. We are talking about the set graph of the function, and graph of the function consists of doublets, where first coordinate is coming from the set x, the second one is coming from the set y. And what is y? Y is the image of x. So what your set is, first of all, let the graph of the function, the map you can say of the map FB. I am denoting this graph by G. So G is what G is? G is consisting of the points of the type xy, the doublets, where y is the image of x, where y is equal to f of x and your x is coming from x. When x is coming from x and y is f of x, obviously y is coming from the set y. So this is a subset of x cross y. Now what we have to prove? We have to prove that the set G is a closed set. Whenever we have to prove that a particular set is closed, it is better to prove that its complement is open. So we will not talk about the set G, but we will talk about the complement of the set G, and we will show that the complement is open. So we will show that G dash complement of G is open. For that, what we have to prove? We will take one point from the complement of the set G complement, some point AB you can say, and we will try to insert an open set, whatever the name you can take, M and P, anything. So we will try to insert an open set M such that the point AB belongs to the set M and M is a subset of G complement, and that will make G complement an open set, and G complement an open set means G is closed. That is the line on which we are going to work. So what I start with, let AB be a point of G complement. So I am taking one point of G complement. Now the property of the elements of the set G, if xy is an element of G, what is happening? Then y is equal to fx. That means if AB is in G complement, that means AB is not in G. So AB is not in G means B is not equal to FA. So this implies your B is not equal to FA. Here A, the first member, is coming from the set X. So this A is coming from the set X. So what is FA? FA will be an element of Y. And B, the second one, is directly coming from Y. So this is an element of Y, this is an element of Y, and they are distinct elements. So B and FA are two distinct elements of the set Y. But we are given that the topological space Y rho is T2 space. And if in a T2 space you are having two different elements, what will happen? You definitely will have two open sets, one containing the first element, other containing the second element, such that their intersection is Y. So what I am going to write, therefore, there exist row open sets. There exist row open sets. Why I am writing row open sets? Because the topology of Y is row. So there exist row open sets. You can say G and G I cannot take because G already I am taking. So U and V, sets U and V such that your B is coming from U, your FA is in V, and the most important thing, that U intersection with V is phi, because of the property of Hausdorff space. These two open sets must be disjoint. So what we are to do now? So we'll move further now. I'm rubbing the statement from the whiteboard because I need more board to prove the theorem. So what we are to do now? Look at, your FA is in V, and FA is in V means your A is in F inverse V. Your A is in F inverse V. V is an open set, row open set, and F function is given to be continuous, and we know that inverse image of an open set under a continuous function is also open. So if V is open and F is continuous, then F inverse V is also an open set. So I'll rename it as W, say W. So A belongs to W is an open set. Is an open set. Why open set? I have told you that V is open and F is continuous. So inverse image of an open set is also open if the function is continuous. So W is an open set. Your U is already open set. So now look there, your A is in W, your B is in U. So where is your element A, B? Your element AB belongs to U and its Cartesian product with W, because your A is in U and your A is in W, sorry. So I'm rewriting here. Your A is in W and your B is in U. So it is W cross U. So AB belongs to W cross U. Now W is an open set, U is also an open set, and we know that Cartesian product of two open sets is an open set. So this is an open set. So W cross U, an open set. So it is an open set, very much clear. Now we will claim one thing. What we are going to claim, I am claiming that this set W cross U is a subset of G complement. This I'll prove now. And to prove this, what I'll have to do, I'll take one element from here and I'll show that the element also belongs to G complement. So I'm taking one element from here, but what element should be here? What type of elements are here? These are the doublets. So I'll have to take the elements of the type CD. So let CD, a doublet, be an element of W cross U. And I'll show that this element CD also belongs to G complement. CD belongs to W cross U means your C belongs to W and your D belongs to U. Now look that C is in W, but what is W? Your W is here. W is F inverse V. So you can say that C belongs to F inverse V and D belongs to U. Now C belongs to F inverse V. This means F of C belongs to V and D is already there in U. D is already there in U. Now I'll have to rub it this line also from there because I need more space. Now look that your FC is in V, your D is in U, but intersection of U and V is phi. So these two elements cannot be same, they must be different. So this means your FC is not equal to D, because if FC is equal to D, then FC belongs to V and FC also belongs to U. That means V intersection U contains an element, which is a contradiction because U intersection V is phi. So FC is not equal to D. Now look that if FC is equal to D, if FC is equal to D, then your element CD belongs to the set G. And if FC is not equal to D, then the element CD will be in complement of G. Where from we have taken this element CD, we have taken it from W cross U and now it is in G complement. So you can say that W cross U is a subset of G complement. And your your AB belonged to W cross U. So AB belonged to W cross U. Now, from this statement, look into the statement this. We have started from here and now we are here. I have taken one element from the set G complement and successfully I obtained an open set W cross U which contains the element and which is a subset of G complement, and this makes G complement an open set. So this means your G complement is open set, and if G complement is open, then clearly your set G is a closed set which was required to be proved. So if you are having a continuous function f from a topological space x top to another topological space which is Hausdorff of y rho, then graph of the function is a closed subset of the Cartesian product of x and y. So this was the first theorem of the day, and after this heavy theorem we will move on to some easy theorems now. So 2-3 easy theorems I will take today because this one was a heavy one. So another, I must not say that is a theorem, you can say an example. Your indiscrete topological space cannot be a T2 space. It cannot be a T2 space. And the reason is very, very much obvious. Suppose you are having a set X and a topology torn, indiscrete topology you can say. So you are having indiscrete topology, and in indiscrete topology there are only two sets. And these two sets are phi and the set X itself. So these are only two open sets there in indiscrete topology. There is no third open set. Now what we have to show that this is not a T2 space if you take any two distinct elements x and y from X. To make this topology T2, what we need two open sets G and H such that X belongs to G, Y belongs to H, and intersection of these two is phi. But we are unable to find these two open sets. Why? Because we are having only two open sets, phi and x. If you are taking phi and x here, then this condition is okay. Phi intersection x is phi, it's okay. But x belongs to phi is a big contradiction. Y may be an element of x. So you are unable to find two open sets, G and H, G containing one element, H containing the other, and their intersection is phi. There is not possible these two open sets. That means it cannot be a T2 space. Now I'll move on to another easy example. I'm not going too difficult today now, because already we have done a theorem which was a little bit heavy. Another thing is that if X tau is a T2 space and tau star, another topology, is finer than tau, then X tau star, this topological space, is also a T2 space. This is also a T2 space, and the proof is very easy. So what you have to prove? You have to take two elements from here and you have to find two tau star open sets containing one containing the one element, other containing the other element, and their intersection should be fine to make it a Hausdorff space, and that is very easy. So let X and Y be two distinct elements of the set X. I'll not talk about this. I'll talk about this. X and Y are elements of X. But this X tau is a T2 space. So you will definitely have two tau open sets. So therefore there exist tau open sets. G and H such that your X belongs to G, your Y belongs to H, and intersection of G and H is Y. This is very much clear because X tau is given to be a T2 space. But another thing is given that your tau star is finer than tau. And tau star is finer than tau means your tau is a subset of tau star. When you are saying that G and H are tau open sets, in fact you are saying that your G belongs to tau, your H belongs to tau. Your G belongs to tau, and tau is a tau subset of tau star, so G definitely belongs to tau star. So if G is a tau open set, then definitely G is a tau star open set. So you can say there exist tau star open sets. Also, your H is a tau open set, and tau is a subset of tau star, so H also belongs to tau star. So H is also tau star open. So that means you are able to find two tau star open sets G and H such that G contains X, H contains Y, and your G intersection H is Y, and that makes your topological space X tau star is a T2 space. This makes your space Hausdorff. So this was a very easy theorem, and I'll take one more easy theorem or example you can say, and then we'll move on to the next video. This video I'll stop here after this one more example. So let us see what the next example we are going to do. It is, you can say theorem, you can say property, you can say example. Prove that every finite T2 space is discrete space. Every finite T2 space is a discrete space. So let us start. So what we have to start with, let X tau be a finite T2 space. When you are saying finite T2 space, what is finite? Your set X is finite. So this means X is finite and your tau is T2. Topology is T2 and the set is finite. And you have to prove that it is a discrete space. Discrete space means that the topology is discrete topology. That means every subset must be an open set. So what we have to do, we will take an arbitrary subset of X and we will show that that subset is an open set. That means every subset is open, and when every subset is open, the topology is clearly discrete topology. So let A subset of X be arbitrary subset of X. I'm not taking some particular subset, an arbitrary subset. Now A is a subset of X, and I'll talk about A complement. A is a subset of X, X is the whole space. Clearly A complement is also a subset of X. But your X is given to be finite. If a set is finite, its subset must also be finite. So this means your A complement is finite set. This is a finite set. And your topology is T2. We have already proved that in a Hausdorff space, in a T2 space, every finite set is closed. So this means your A complement is closed because every finite subset of a T2 space is closed. The reason I have written here. Now your A complement is closed. If A complement is closed, then your A is open. And what was A? A was an arbitrary open subset of X. And we have shown that it is open. That means every subset is open. And when every subset of a topological space is open, then what the topology is? The topology is discrete topology. So this is a discrete space, and that was what we required to prove. So I'm going to stop this video here. In next video, we'll be here once again with more theorems on T2 space, and then we'll move on to the regular spaces, T3 spaces, T4 spaces, and so on. Till then, thank you once again.